Hi, guys. Thank you so much for being here, for joining us for Galileo Science Cafe tonight. We have a really wonderful talk planned for you, and we're so excited to kind of introduce you to the talk tonight. Before we get started, though, I do have one thing I want to share with you. Tonight's talk is actually being sponsored by Mason's nanofabrication facility. And so I do have two folks, Amy Adams and Sean Wagner, I want to invite to the stage to tell you a little bit more about that facility. It has a lot of really cool tools for students to use to do really cool things like you'll hear about in tonight's talk. So I want to have them come up forward, kind of share with you about that facility, and then I'll introduce our speaker. Come on up, guys.
Thank you so much, Amanda, and I'm really excited for Ethan's talk this evening. You're all in for a wonderful treat. My name is Amy Adams, and this is my colleague, Sean Wagner, and we just want to take a couple minutes to tell you about a new program that we have here at George Mason University, and we're hoping that you will help us in sharing it with your friends and your family and the others that you know. We have a new clean room facility here at Mason, and Sean can talk more about what's happening in that space. But essentially, it aligns with what Dr. Ahn is talking about and where he does his research. We want to give an opportunity for folks to enter this type of workforce, those who may not have had that training or background. This could be individuals working at Walmart. This could be individuals working in healthcare. This could be individuals in any area of work that says, you know what, I want to try something new. And we realized in doing this has got to be a risk-free way, right? So what we have done is we are offering Nano Boot Camp. Two offerings, one in August and one in September. You can find this on the web at nff.gmu.edu. We also have flyers, but we're offering this for $150 for individuals to come in, gain hands-on access in the clean room and learn about the types of tools and processes that go on to make technologies like you are going to hear about tonight. We also have a program, Nano Camp, running in June for high school students. We have 2 more openings left. I would love to thank our colleague, Eleanor Wagner, who has been spearheading these outreach efforts. And I'll turn this over to Sean just to talk about the types of things that folks will learn in these camps, which will give you an idea of the types of things that are in this facility.
Thanks. During the week that we're there, you know, the students' time will be split up between the classroom and in the lab proper. I should move over, I guess. So in the classroom, we'll learn about the techniques that are common throughout the semiconductor business. And, you know, deposition and etch techniques, photolithography techniques that you use to create these tiny features on the wafer. And the times that we spend in the clean room, that other half of the day, roughly, we will actually go into the clean room and the characterization lab and use the instruments to do some of these things within some safety guidelines, because some of the materials can be very hazardous. So my team and I will handle the actual dipping of wafers in acid and things like that. But the folks will be there and get to see it all. And that's pretty unique. They'll gown up, they'll go in, have a really good time. There's still a little magic in the world when you see a pattern develop out of nothing right in front of you. And we have some of the top of the line characterization tools in the lab right next door that people will be able to use to image these tiny features that we make. So it's a great opportunity. The cost basically, and just barely, covers you know, the materials and the gowns and all the stuff that we need to go in and out of the clean room. And I believe there's a tuition assistance if someone needs that. So you can, you know, pass that along to anybody that may be interested in learning about it.
Yep. And the reason we're doing this is we know there's a demand for a workforce in this area. And so at the end, participants will also meet with employers, local employers who will share what their jobs are like, and then also connect with the participants to hopefully identify some opportunities for employment. So thanks for giving us this opportunity, Amanda, and really delighted to be here at the Galileo Science Cafe and learn about Ethan's work.
All right, I have my cheat sheet ready to introduce our speaker tonight and his illustrious bio. So this is Professor Ethan Ahn. He joins us Originally, he was an assistant and then associate professor at the University of Texas, San Antonio. So we definitely poached him. It was a win for us. So that's super exciting. He got his bachelor's and his master's in electrical engineering. So he's an electrical engineer from the beginning and on. I also want to share that he has an NSF EAGER grant that he got. If you're not kind of in academia and don't know what that is, these are really, really competitive grants for kind of the top performers in their field. So this is incredibly illustrious work that he's done, and he's done a really good job kind of bringing it down to a level to democratize what he's doing and make sure everyone can kind of understand how cool it is. So I'm really excited to present Dr. Ethan Ahn. Please join me and you can get started with the talk.
Thank you for the introduction. How's the food? Great. Okay. So I hope you didn't come here just for free food. Okay. I mean, nothing wrong with it, but as long as you decided, staying longer for my talk, I really hope you can enjoy the talk and also you can learn something so that you can feed your brain too. Okay. So about a week ago, why is it not moving? Let's see. Can I just click over here? I can do it here, but very okay. So about a week ago, Sam Altman, who is a co-founder and CEO of OpenAI, which I believe is very well known for ChatGPT and everything to everyone, right? So I think he was talking to his investors in some meeting that he wanted some fundraising of $7 trillion for the technology called AI semiconductor. What is that? Okay. When I saw this news for the first time, okay, so I was really like surprised to hear that because $7 trillion seems like much, much more than the whole sales volume or the market size of this whole semiconductor industry in the world, okay? And of course, there were a few comments from others, like I think Jensen Huang, who is a president of NVIDIA, who is now making a lot of money for AI thing. But then he commented like, oh, no, we don't need that money for, again, AI semiconductor. So what is that? What is AI semiconductor? What comes up in your mind when you hear that? So by the end of this talk, I really want you to have a better idea of what they meant by that, okay? Let's look around, So I'm sure you can maybe find a few of your friends or family members who are currently working on computer engineering or computer science, or has worked on that before, right? But then you may ask, what are you working on? So then I'm sure you a lot of times hear that they work on AI. Okay, that's true. I mean, right now, either in computer engineering, computer science, or any other disciplines, electrical engineering, bioscience, okay? A lot of people are doing AI. So then you don't stop there. You have to ask follow-up questions. So what specific domain are you working on in AI? Because in any discipline, I believe you may either work on software or hardware. Make sense? Okay. And then whether they are working on software or hardware in AI, then I'm sure 99% will say we are doing something on software because you see them like coding, programming, working from home every time. Doesn't have to be in a lab, okay? But then what about hardware? What's going on in hardware? Are we good for hardware? Do we have good hardware for AI? Okay. So that's something I want you to think about. And this talk is going to be a little bit on that, okay? So I think this whole story, like about this Sam Altman and many others in this area, why they keep talking about AI semiconductor and what's going on. So that's gonna be a good hint for today's talk. So when you hear about AI, I believe this is maybe the easiest one that you can think of, okay? What's that? Roomba, okay. So the robot cleaner, okay? So this guy is kind of doing AI thing, okay? I'll touch a little bit more on that in a minute, but this guy has been good to make your house clean and navigate through and then draw some map, based on some algorithm, so on that. So that's cool, okay? Next, what about this? So if you are following up any like scientific article, like this was introduced last year by what is called MIT Technology Review. So they introduced like a few advances, breakthroughs in the area. But then last year, they just told us, okay, because of this AI, we were able to solve some math problem that has not been solved in history. So in each area, I believe there is long standing problems that we're trying to really solve, but we are not able to solve for some reason, right? But then AI just help us to do that. Okay, I think a team of researchers in Google, they use some sort of AI software to do this. That's cool. You know what? Even if it's true that a lot of things here in AI are driven by software again, but don't forget that this real world that we live in, every single piece of this real world is made of some materials, right? Okay. So we need materials, we need to discover new materials, we need to make better materials, blah, 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 right? But then this AI even is helping us to discover some new materials for this world, okay? So that's gonna be like a major, like a change, in many different areas, okay? Like electronics for sure, biology, construction, transportation, energy, power, just name a few. So I'm just introducing a few like highlights that we had in the world of AI, which makes us excited, okay? So that's good, right? But as you can imagine, there is a little dark side of AI too, as you can imagine, okay? So a Roomba recorded this woman on the toilet. And because this Roomba was connected to internet, right, through Wi-Fi. And then this picture was maybe sent to somewhere, okay, some cloud or data center. I think the very early version of your Roomba, just came with some simple like IR sensor. So meaning it just transmits some infrared light, okay? So they just receive the reflection so that they know, oh, okay, so there's something, but they never knew what is it. Okay, they can figure out there is something, but they didn't know what it is in their early version. But I think since the mid 2015 or 16 or so, they really had this AI technology in there, what is called image recognition. Okay, so image recognition is a well-known subset of AI. And since then, this Roomba had this high definition camera. Okay, so they can really capture all the images. And because of AI, they can even figure out what it is. Is it human being? It's a toilet, okay? It's a desk, okay? So they can figure out what it is. So then the problem is, again, these privacy issues, okay? So always, is it really good to have this AI? But they are helping us, but is it really right to do it like this? Anyone saw a Super Bowl last Sunday? I'm sure many of you did, right? Okay, good. But then you should have seen her also, Taylor Swift, okay? One time I read an article about her, like her previous concert. There's dating back to, I think, 2018, so a few years ago. So she had a concert in California. And then there was a little bit of issue related to AI, okay? So the thing is, she had this kiosk where all the attendees, they are supposed to check in, right? So they come to the kiosk and then enter some information, right? But then the problem is the team had this hidden camera attached to the kiosk. So the kiosk took the pictures, to take the facial photos of everyone coming to the concert. And then these pictures were sent to some data center. They did that because what? Because they wanted to track some stalkers, okay, in her concert. So the issue is, the point I'm trying to make here is, okay, I'm just wanting to say, okay, so AI is doing good for sure, no doubt on it, okay, but there are a little bit of ethical issues, okay, some privacy concerns. If you go a little bit further than political issues, societal issues, there are many issues, okay? But we are not here today, okay, to talk about those issues because we are all scientists, engineers, right? So you are all rising scientists or used to be a scientist, engineers before, right? So I'm here to talk about technological issues, okay, behind AI. So let's look at this robot. So he's messing things up, okay? Okay. So you heard about this company who made this robot called Boston Dynamics, okay? So as you can see from its name, it is a spin-off company from MIT. Don't get me wrong, okay? So I'm not trying to say their robots are bad, okay? So what I'm trying to say is the technology associated with even AI, okay, is still, in my opinion, very, very far from the level that we want. What about this? Everyone knows what car brand is this, okay? I didn't say it's Tesla, okay? but you know what it is, right? So if you look at here, then we have this pretty, beautiful full moon, okay, in the evening. But for some reason, this navigation system got it as a yellow traffic light. That's weird, that's funny, okay, but that's even dangerous, okay? So something is going on like in this state-of-the-art AI technology for sure, okay? So we don't know if that's really triggered by any software error or hardware error, okay? I'm not quite sure yet, okay? But certainly you can know, oh, so we need to do something better, okay, for AI. So that's the whole thing. So today, before I wanted to a little bit go deeper, okay? In my opinion, the reason that we are taking full advantage of AI for now is because we have all these three different elements all in place. So specifically, I'm talking about machine learning, okay? So this is a subset of AI, okay? So where you are trying to train your machine, train your computer so that they can behave the way that you want, okay? Like you train your dog. In order to do that, we need these three things. Okay, so the easy thing first, okay, so this data, because we are training them, okay, we need data, okay, we need a lot of data to feed to your computer so that they can learn, okay, that's good, that's easy. But then let's look at the other two, okay, so as you see, learning rules, algorithms, models, okay. So which one comes to your mind? Like at the beginning of this talk, I said any discipline has either software side or hardware side, okay? So does it belong to what? Software, okay? So everyone knows that this is related to software, okay? And then on the hardware side, we have what is called GPU, okay? Graphical Processing Unit. So if you Google, if you ask around, if you do your own research, if you listen to any talk, okay, you will see a lot of people in this area are working on this side. Okay, so they are making a lot of new algorithms, models, learning rules, okay? So they are really making things go forward in terms of software. Okay, we have a lot of great scientists, neuroscientists, computer scientists, computer engineers, all doing that. What about hardware? We have GPU. Who is making the best GPU right now? NVIDIA, yeah. So that's why they are making a lot of money right now. But other than NVIDIA, do you see any other options that can maybe replace GPU for AI? No. We only have GPU. That's probably why Sam Altman was saying, oh, so we need something else, So we don't want NVIDIA maybe to win all, okay? What I'm saying is GPU is good, okay? GPU is good in terms of speed performance, okay? So it accelerates a lot of AI tasks for sure, but in terms of, let's say, energy efficiency and many others, I don't like it, okay? Because I feel like I could make it better. So now the balance between software and hardware is not good. So think about this, what do you think is gonna happen if you have a software that is very, very good, state of the art, cutting edge, very nice, but your hardware is kind of old school. Okay, you run this software on this hardware. What do you think is going to happen? So let me take maybe the best, easiest example that I can think of for those who do not have any technical background, okay? So let's say you have Mac OS, which was released like a few years ago. Okay, Ventura, which is pretty good one. Okay, which is still running now. But then for some reason you have your hardware, your laptop computer, which is like a 10 years old. Okay. So MacBook Pro 2012 combined with macOS Ventura 2012-22. What do you think is going to happen? See here? It's gonna just keep loading. You know what? Theoretically, I don't think this is even possible. I mean, it is prohibited, I think. But because we have so many like young scientists, you know, who is really good at programming, coding, and all that. So let's imagine we managed to somehow install this on here. But then I'm sure, you know, I bet, okay? So you have some issues, right? More technically, this is what I can tell you. If you run a good software on bad hardware, so then this is what happens. So think about your computer, okay, conventional computer, how it is structured. So when you open up your cell phone, laptop computer, desktop computer, any computing system, then they have three major parts: logic, memory, and interconnect, okay? And in this part that we call logic, where you have CPU, GPU, you know, this is where this computation happens, okay? And then you have memory or storage, like, you know, main memory, RAM, SSD, okay, if you heard about. So then if these two elements, they got physically separated in your computer. This is the area for CPU, okay? This is the area for memory, okay? And then they communicate through a channel called bus, okay, BUS, okay? But then the problem is, if your software is really super nice, I mean, they can handle with a lot of data, okay? It's very sophisticated, okay? It kind of functions like our human brain, for example. If you run that software on that old school hardware, then what happens is this. See here? Let's say you put 100 of your time, 100 of your energy to do some task, right? But then 96% goes to data transfer. What does it mean? So this CPU and your memory, they have to communicate, and the data needs to go back and forth, right? That's going to consume your 96% or almost all of your energy and time. And only 4% is actually used for your work. Don't you think it's too bad? Very inefficient, terribly bad? Okay, it is, yeah. So this is, I mean, these numbers, if you believe in these numbers, we need something else for hardware, because this is what happens because your hardware is still old-fashioned, right? So if we do not like GPU, okay, I mean, I have nothing bad feeling for NVIDIA, okay? Actually, I knew that NVIDIA is gonna really hit when I was really young, but I regret, you know, not buying a lot of stocks of NVIDIA. If I did that, then I would earn a lot of money. But, you know, if I don't like GPU and if I believe, okay, so we can maybe make something better than GPU, okay? So then is there any reference, or is there any technology, or is there anything that we can maybe reference, we can maybe learn, we can be maybe inspired by, okay? That's, interestingly, us, human brain. Okay? You know what, in history, I think people were always like excited about, okay, so what about we make a human being and computer match? I mean, compete for something. I think there has been a well-known chess match between computer and human being, and I'm sure computer won. And they got excited, oh, so we made great computer, okay? But then more recently, you know, in this traditional like board game called Go, which requires a lot of brain processing, and see here, you know, how many, I think, this is only like time left, but it takes hours, okay? It's kind of very complex game. But then they got interested, oh, okay, so what about we make this game competed by the state-of-the-art supercomputer in the world, best of the breed computer in the world, okay, AlphaGo AI computer versus the legendary human champion. Do you know who won? Anyone? So computer one, okay? I believe, I believe it sounds crazy because I said, oh, so we need to look at our human brain, but computer one. So computer one, yeah, right. So they had 5 matches, 5 different matches, and I believe the score was 4-1, okay? So the computer won 4 times, and human won only 1 time. So you're right, so computer won. But I'm not really interested in who won in this game, okay? As a scientist, as a researcher, as an engineer in this area, I'm not interested who won. What I'm interested in is these numbers. If you believe in these numbers, see here, this is the power consumption that the computer used and the human used, okay? So in order to do this game, same game, okay, the computer should spend 100 kilowatt of power versus, believe it or not, human being, our human brain is consuming only 20 watts of power. That's many orders of magnitude smaller, okay, in terms of power consumption. What do you think now? Okay, so I believe in terms of energy efficiency, okay, human is the winner, I think, okay. And scientists understand exactly like why, okay, how come. So human brain consists of what we call neurons, okay, and synapses, and we have billions of them, okay, not 100,000, million, okay, billions of them. And then each does its function, like neurons are like CPU and GPU, where we do computation, okay? And synapse is where we have memory and learning, okay? And we have billions of them. And the thing is, they are like entangled in a very complex way, and they spread all over the place in your brain. Do you see the difference? So if you got my saying that in a conventional computer, okay, so you have CPU and memory, and they got physically separated, right? And then they communicate through a short and narrow channel, right? But then I'm saying for human brain, the neurons, which is kind of CPU, and synapses, which is kind of memory, okay, so they are entangled. So that means, do you think like our human brain is like, okay, so left side of it is like CPU, and the other half is memory. Is it like that? No, okay. Of course, I mean, different parts of our brain is doing some different functions for sure, I know, okay. But we have neurons everywhere. We have synapses everywhere, right? Okay, so they all spread out all over the place, okay? That's the key difference from how computer is structured. And that's why we are very good at some tasks that require a lot of parallel computation, okay? So there are so many people like me, okay, who are interested, inspired, motivated by this fact. So, hey, then what about we make a computer, okay, that computes, okay, exactly in the same way that we do, okay, the way that human brain does, okay. So this area is called brain-inspired computing because we are inspired by brain, or bio-inspired computing because we are inspired by bio, or someone called it neuromorphic computing, okay. Neuro means, I think, basically bio, okay. So this is one of the research that I'm doing, and also a lot of people are doing. So at this point, I want to take some moment and then let you think and then ask some questions. Does it sound really possible? I mean, if you get it, then what I'm saying is, we want to make some real thing, like device, okay, that behaves as a neuron. It's not real biological neuron, okay, but it has the same function as a neuron, for example, okay. It behaves as neuron, okay. What neurons can do, they can be basically implemented in the same way in this device. Let's say that, okay. We want to make that neuron device, okay. And also we want to make synapse device, okay. And how many I said we have neurons and synapses in our brain? Billions, right? So I said, okay, I want to mimic, I want to copy my brain and then bring it to my real computer hardware, right? So then does it mean that I'm trying to make billions of these devices? Again, one of them are acting as neurons and the other is acting as synapses, okay? Does it sound really possible? And then people are crazy here, okay? So we don't stop here. So once we make them, we want to put them all together, billions of neurons and billions of synapses and all them together into a microchip that is hopefully maybe as small as my thumb. See what people are trying to do? Okay. So does it really sound possible or crazy? Okay, like sci-fi? That's where nanotechnology comes in. Okay. So if you look at a chip, okay, which is as small as a coin, okay. Back in 1960s, we only had 4 elements, 4 transistors in here, okay. But then after 60 years, the number of transistors, believe it or not, if you take out any like a microchip from your computer, okay. So in 2020s, we have billions of transistors, billions. Can you come up with any science or engineering technology that gave you like a billion times better enhancement over only 60 years? Other than nanotechnology, other than semiconductor? Then let me know, please let me know, because I can't come up with anything other than this, okay? So what I'm saying is nanotechnology has been with us, okay, has existed, okay, and then they were doing their good job, okay, in making things smaller than previous year, smaller than 10 years ago, okay. They keep making smaller and smaller, and then put them all in one place, which is very, very small. That's not new, okay. So we already live this world with this technology. So then the point is, because we are talking about AI, right? So then what about we use this nanotech to do something good, okay, in this regard? So what I'm saying is fabricate some devices, but they can behave as neurons, some devices that can behave as synapses, but both are nanoscale. Okay, so sounds now possible, right? So you feel better. So this is again one of the research topics that I'm doing here at Mason, and like Amy said, I mean this facility here that Mason has in this Manasses, the nanofab clean room is going to be the major key factor that let us achieve this research goal, okay? Sounds boring? Good? Good? So far so good? Okay. So I'm not like neuroscientist or biologist, okay? But let me talk to you a little bit more about our brain, okay? Because I keep saying, oh, so we are so much inspired by how brain works, right? So this is a cartoon for what we call a neuron, okay? Neuron cell. Forget about all these terminologies, okay? And then this end, again, because this neuron is going to be connected to another neuron, right? So then the tail of this neuron and the head of another neuron, they're gonna be connected. And then that area is called, again, synapse, okay? So this synapse is really important part of our brain because that's where this memory happens. It's where this learning happens, okay? Because we have to learn how human learns because we want to, what? Train your machine so that they can learn, okay? How come we make them learn without knowing how we learn, right? Okay, so in biology, it's called plasticity, okay? And in electronics, it is called connectivity, conductivity, okay? But forget about these terms, okay? I think I have much better way to explain this because everyone knows, I think, or about this Pavlov's dog experiment.
Amen.
Anyone didn't hear about this? Yeah, ring the bell, yeah. So, and then what happens? The dog salivates, right? So in order for, I mean, for those who are not familiar, just in case, okay? So what happened here in this experiment is, you got a dog, and then you know that your dog will salivate when he is given a food, right? Okay, But then they did some experiment. Okay, what about they give the food and at the same time, they ring the bell. So here the point is at the same timing.
do that
That's
with
the most
Snoopy.
important thing, okay? So if
You do
the
that with
dog
Snoopy.
sees a food and also hear the bell ringing, okay? So then, because still he got it, he got the food, so he will celebrate, right? And then the interesting thing is, what if we get rid of the food, right? So just ring the bell, but then people saw the dog will still celebrate without the food given, right? Okay, so that is what we saw here in this experiment. And that is well explained by this theory called neurons that wire together. So what does it mean? So it means in this dog's head, there is a neuron, for example, that is being activated or stimulated when he when he saw the food, okay? And then there's another neuron that is activated when he heard the bell ringing, okay? But then because these two stimulus came to the dog at the same time, that's the important thing, okay? Because of that, these two neurons are somehow connected, okay? So these two neurons connected and then they behave as one whole thing. That's why. Let me give you maybe a better example here. So I think in this seminar series, I really wish I could also come. And my physics faculty colleague, who is a professor here at George Mason, who is doing a lot of research on quantum computing and all that. I think Professor Patrick Bora, right? So he's going to give, I hope, very nice talk in the next, right, in May, right? So you will know a little bit more about quantum, okay? But what I'm saying here is, even if I'm not physicist, because I'm working on nanotechnology, sometimes I need to teach students what is quantum mechanics, okay? But then always I feel like, okay, it's very hard to teach because they already have in their mind, quantum mechanics is hard. So they're kind of scared already, right? Do you know why? Do you know why a lot of people have this in my mind? What happened in their brain? The way that I understand it is this, okay? So there is a neuron, okay, in student's brain that is activated when they hear quantum. So let's say there is a quantum neuron, okay? And there's another neuron next to it, right? But then this neuron is activated when he hears something hard. This is a hard neuron. Let's name that, okay? But then when someone say, oh, okay, so maybe your friend, okay, and talk to you, hey, quantum mechanics is hard. Okay, if someone hears that, okay, so then what happens in your brain is because these two neurons, again, they got stimulated, they got activated at the same time. Again, that's the most important thing, okay? Because these two neurons are stimulated at the same time, they start getting connected. Okay, so you may believe, oh, so this is a little gray color purposely, okay, because it's still likely hard, okay? But what about a friend of friends, parents, grandma, okay, and maybe your teacher, okay, keeps saying the same thing over and over, okay? But then these neurons again keep being stimulated again at the same time. So then this connection becomes even stronger. So in your head, okay, so these two neurons are one thing, okay? So that's why you think quantum mechanics is surely hard. And at this point, you think this as learning. At this point, you take this as memory, okay? And this is happening again where, this is happening in the place that I call again synapse. Sounds good? Okay. Of course, we know humans always change our mind, right? Okay. So if you don't hear that often, then maybe this connection will get loose. Okay. So maybe at some point later, 10 years later, unless you keep hearing this again, you may think, oh, okay, or it's not very hard, or maybe even forget about it because these connections get loose. Okay. So it's all about, again, these two neuron cells are how well they are connected and how often these neurons are exposed to this stimulus, okay, in terms of timing, okay? That's all that's what happens in our brain in terms of this technology. So sorry about this busy slide here. You know, when I was asked to give this presentation, I was looking at like, because this was supposed to be like TED type talk. And then I was reading about, you know, all these instructions that are given to real TED speakers. And then I learned that don't put any text. And your text font size is, you know, is supposed to be even like a greater than 42. Wow. So I really try my best, but again, this is the worst slide in that context. But the point here is, this is the type of device, okay, that can be that kind of synapse, biological synapse, okay? So let's see if I can give you better explanation here. So you have this electrode, okay, lines that go like this way, okay? You have another electrode lines that go the other way, which is perpendicular or cross like this, okay? And then you have something in between, that is this, okay, whatever material that we call GST, but forget about its name, okay? So then, isn't it like similar to how neuron and synapse is structured, okay? So if we think, oh, okay, so this top electrode is like a neuron, one neuron, and this bottom electrode is another neuron, right? And then they are making some interface here. So what about we call them? What is the name of the neuron and neuron interface? Synapse, okay? So what about we call this the synapse? Okay, oh yeah, so it makes sense, okay? But then, you know, the people, you know, really made this kind of structure and then, you know, tested if it really has something similar to what real biological synapse does. And it turns out to be yes, okay? So we can actually emulate, we can actually mimic almost all functions and features that biological synapse has using these electronic devices and structures. Of course, in order to do that, we need, again, nanotech, okay? Because we need to grow the materials, we need to make devices, okay? We need to characterize those devices. This is all nanotechnology. And then again, these individual devices, okay, are supposed to be, okay, so I have a few more minutes, okay. And these devices are supposed to be, again, packed into a microchip. That's what's been done already in this area, okay, believe it or not. iMac. Does anyone not know what is iMac or where is it? So this is a research center, research consortium kind of, located in Belgium. And they're doing really good microelectronics and many other research. And then they made, back in 2017, some chip that can like self-learn like human being, and then they can even compose a music. Okay. And here in the United States, we have IBM very proudly, okay, because they are one of the leading industry, in my opinion, in this AI hardware area. And they also made some kind of new version of AI chip that is called or named North Pole. Okay, so they do some AI computation. And of course, this is not as small as my thumb or something that is small enough so that it can be packed into my phone, right? So still lots of things need to do. And also, if you look at inside, then I don't think they have a lot of interesting materials inside here. Maybe my best guess is maybe some part of it is pretty new, okay? And maybe some other part is still old and they kind of make some hybrid version of, you know, those materials and devices inside, I believe, okay? But then again, as a person who thinks forward, okay? What about 10 years later, 20 years later, 100 years later, okay? I hope to see, you know, those emerging real nanomaterials inside these chips. And these are the examples of materials that I grow and I research and I develop in my lab. For example, metal oxide, thin film, chalcogenide, thin film, ferroelectrics. Hello. Okay. Nanomagnets, blah, blah, blah. Okay. So there are many candidates. These are again all, what happened here? Okay. So these materials are supposed to be all nanoscale. And supposed to have some very nice characteristics that we don't find for large scale materials. So at this point, when I finish up making this slide over here, okay, so I thought, okay, so should I really go deep dive, to talk about what it is? So I talked to myself, oh, no. So maybe I should stop here and then maybe, try to bring something newer, or they can give you a better, bigger picture on it. So I decided to do it. So what I'm saying here for the maybe last few minutes is, as a researcher in this area, because we have many like emerging candidates, no one tells you which one is going to win, right? Who knows? Okay, so maybe in 10 years later, 20 years later, we don't know who is going to be the winning technology. So we have to really carefully look at them, right? Which one has like what is pros and cons for each, right? So for this AI, I think I wanted to give you two major criteria that I always think of, okay? So when I, again, choose what material to work on, what device structure is going to be made, I always think about these two aspects. Number one is this, application, okay? Specific application. I mean, AI, but everyone knows AI. So where at? Did anyone hear about edge device? What is edge? AI, so you kind of have some sense of what AI is. Device, shipments, category, okay, so they all look good. What is edge? So here in this like internet network, right? So massive network where you have data center, maybe at the center, right? And then they all like branch out, coming to you, right? Coming to the user and the user, right? So then the edge device means any device, okay, that is physically like connected to you, to your, to the customer, okay? So that's the edge of this network cloud, okay? So for example, like, okay, so mobile phone is definitely one of them, which is a major thing. And then maybe drones and PCs and some head mount display, so all these things. So the point is all these devices, in order for them to have AI, and then have state-of-the-art hardware like we talked today. But then the major concern is energy consumption again, okay? If it were in data center, I wouldn't worry about energy, okay? But if it is going to be something that is going to be on my phone, then I have to worry about energy because I cannot afford, my phone cannot afford like 100 kilowatts, right? Okay, so we always have to make sure the new technology that we are developing, okay, they have right energy efficiency because we are targeting this application, this specific application, okay? And the second thing is what we call endurance, okay? So if this terminology is too hard for you, so then let me explain this way. So if we keep like training your machine, right? So then we need data, okay? So then what happens if you give the data to your machine, but then your machine or computer doesn't behave the way you want? So it fails. So then what are you gonna do? Train again, right? You can train again. So give new data set and then see what happens, okay? So these things like need to be taking place like over and over until the machine gives you the right answer that you want, okay? So then we have to keep programming your computer, your device, and then if the result is not good, then erase it, and then do it again over, okay? So this cycling should happen many times, and how as many as this number, believe it or not, 10 to the 15, okay? I think million, billion, so this is 1,000 trillion, okay, 1,000 trillion times, okay? So you want to make sure your device that you use as, again, neuron device, synapse device, okay? But that you want your device not to fail until you do this much of cycling. Sounds crazy, right? But then, wait. Yeah, so these devices that I listed up, they can do it. Okay, they have potential to this job, to do this job. Okay, that's why people are so much interested in researching these materials. So this little website is my Google Scholar website. Sorry for those who maybe expected to hear something more like a technical or professional detailed talk. Sorry for that, but you can always Google my name, Ethan Ahn, followed by Google Scholar. Okay, so then you'll see a full list of my works. Okay, I'm kind of naked, you know, in this sense. I cannot hide anything that I did from you. So feel free to navigate through, and then if you had any questions, want to something like you want to discuss, feel free to reach out to me at any time. Okay. So I like to conclude my talk by saying science always likes to go two ways. I don't know if you agree, okay, but this is what I think, because what is the Newton's third law of motion? Anyone? Action, reaction, okay? I think I heard something from the back, okay? Action, reaction, what is that? So if there is any action, then there must be reaction of the same amount, but opposite direction, right? So if I, for example, push this desk, okay? So then this desk is going to push me also with the same force, okay? So that's Newton's law that almost everyone knows. So it's two ways, okay? Let me give you this example here, because you know at this NSF campus, there are a lot of biologists and neuroscientists here who is doing a lot of research and teach on biology and bioengineering stuff. If you think of nanotech along with biology, okay, so then traditionally, like nanotechnology has been helping biology a lot. You know, remember this direction. It's going from nano to bio. Okay, so here in this picture, I think this is a kind of nano-sized structure hole where you can do some DNA sequencing. Okay. Don't ask me what is DNA sequencing because I'm not on this area. Maybe you can find someone else to ask, but I know that this is used for DNA sequencing. And this little like funny shaped biological cell, which I know is called dendritic cell, which is responsible for your immunity reactions and all that. And this little spiky things, this is silicon nanowires. Silicon, you heard about it, right? But that is structured in that nano shape. So we use this material to deliver RNA. Okay, you heard about DNA, RNA, all this stuff. And here on the right-hand side, this is what we call microneedle array. This is actually one of projects that I'm also working on. And you know, when you get this shot for your flu or COVID vaccine or whatever, we use a big, scary syringe type needle, right? So it always hurts. And also it takes some time for you to see some effect, right? But then scientists like to make some kind of patch-like device where the needles are shorter. So the needles do not touch your nerve cell. So the point is you don't feel any pain because your nerve cells are not touched, okay? And then instead we have an array of them. So we have many, many of them, okay, that can cover a wider range so that maybe hopefully as soon as you get this vaccine or medicine or whatever, you will feel that effect almost immediately, okay? So that kind of research is being advanced again with the help of nanotech, okay? I mean, this is nothing new. I mean, this has been like a study like a long time. But the point I'm trying to make is, what about the other direction? From bio to nano, can biology do something for nanotech? What is this? Cicada, okay? So you have a cicada, and if you look at its wing, that is zoomed in here, okay? But then people found that this wing has certain pattern, okay? It doesn't, look like some structure, by naked eyes, okay? But if you look at it in microscope, then it looks like hexagons-like structure, and then its size is a few hundred nanometer. Wow, okay? And believe it or not, this is mechanically as strong as wood, okay? So it's Young's modulus, which is one of the indicator for how strong it is mechanically. So it is pretty high, okay? So it's strong, it is nanoscale, it is patterned. So we like to use this for maybe nanofabrication. So we can use cicada wing to make nanoscale devices. Okay, that's really what's happening here. Again, from bio to nano. And this area, generic area, where we like to learn from biology, learn from nature, to do something good for science. This area is called biomimetics. Okay, I don't know if you heard about, but that's really one of rapidly rising research area, in my opinion. So same thing, it's happening for nano and AI. Okay, so again, AI has impacted a lot us, like in many different sectors of society, including nano. But then now it's time to help AI. Okay, so and I think nanotechnology can do a lot of good jobs to make a better AI, in my opinion. So that's my talk, and thank you for your attention. And I'll be happy to take any questions if you have any. Thank you so much. Yeah.
Thank you for the talk. First of all, it's really interesting. My question, so from the materials that you showed there, what makes a material a good candidate for AI semiconductor or for it to be used in,
Yeah. So yeah, so I told you that I'm looking at two criteria here. So the quick answer for that is it is very energy efficient, and also it can have very long lifetime. So it can endure, it can withstand, it can bear like up to like 10 to the 15 cycles when you do training, okay? And also because it has so high energy efficiency, so it can be hopefully put into your mobile phone, for example, okay? And I mean, in order to echo with that, you know what, you may wonder, like, why do we need something new? If you ask that question, I mean, which I often hear from other students, like, what about we have like a silicon already, right? So we have silicon everywhere. But then what about we just make silicon small? Just thin it down, okay? Make it small. So then can it be used for AI or whatever? Okay. So then I always say, hey, you know what? The big size silicon versus small size silicon, they're completely different material. Okay. So when you make some material to be nanoscale or even smaller than that, it's not silicon anymore. Okay. So the characteristics that you thought is good for silicon is no longer valid in that small scale. So that's why we don't want to use any existing material. But these materials that I listed up here, okay, of course, there are a few more. This is not all, but these are not like that. Okay, so even if they are nanoscale, they still have characteristics that we want. Okay, so that's why we don't want to use silicon or any other existing materials, but we research new materials. Any other questions? Yes.
High level question, consciousness, AI with consciousness, is that a hardware or a software problem?
I think
And
that
if you have enough density, you're gonna automatically have consciousness?
I think both, I think. Yeah, so I think a lot of people, they like to address the problem by making the software better, for sure. And I think I've seen a lot of success in that AI consciousness. But again, the point is, you know, when you bring that onto whatever hardware that you have on your hands, then it's a different story. So then always there should be hardware that can back up, or I mean, provide enough support for it, in my opinion. So should be both problems, I think.
So when you have these systems of basically a CPU and a memory system interlaid together, typically CPUs, very high frequency switching, very high temperature operation. Do you have any worries about thermal or electromagnetic crosstalk from your CPU aspects over to your memory, messing up the actual memory storage of your device?
So I think you are asking so many things in one simple question, but I'm trying to process in my brain how to best answer that. But the thermal problem, for example, is always here. Whether you are working on silicon or any other conventional materials, or even these new materials, you're right. So if you have them like so close to each other, then they can crosstalk electronically or electromagnetically, thermally. So they always talk, and then that's an issue, well-known issue that we are trying to solve. I'm not trying to say that for this new problem, new materials, that's for any materials that you are going to work on. And I think, we have to be a little bit careful when you say that, because the separation that I said, the physical separation between CPU and memory, that's like on the different scale though, so that's like a few centimeter or a few tenths of centimeter separation, right? But then now here you have like a nanoscale materials, and then you have another nanoscale materials, and there is the separation between them. That's also nanoscale, okay? So then the factors that play into here, they are all different depending on what dimension you're talking about. But my quick answer is yes, we have still that kind of issues a lot, and we need to solve that for sure. Yep.
So the kind of design you're working on, or the general type, instead of binary, is it more of like an analog style weighting? And are there any algorithms about the work with that, or that's still a work in progress?
Sure. You're right. So I think one thing which I didn't talk today is I should talk a little bit more about that when I talk about synapse, because you see here, this is going to be an analog valve, like you said, not digital valve. So here, the hardware we are working on, they should be able to both do digital and analog. So in a sense that they can be like a 0 and 1, so that you can take it as like a binary memory or something. But then also we want them to be like a programmable, like grayscale. So very high, little bit high, some medium, okay, very low, very, very, very low. So we want them to be like changing their state in a grayscale too. So that is a requirement for this AI hardware. So that is the most important characteristic that we are looking for when we work on anything new device or materials in this area. Did I answer your question?
That's pretty much it. So like on the current situation, does it count for deformation on like having slightly different inputs and modifications and processing it?
In order to have more grayscale or non-analog characteristics in there? Yeah, sure. Yeah, absolutely. Yes. Yep.
With more tech going into like things like spintronics and experience have racetrack memory, so you don't need to go into the memory to do all those computations. How does neural networks here compete against something that could be like programmed like that?
So it looks like yeah, so this question came with a lot of pre-knowledge, in this area, because he's saying spintronics and racetrack memory, which maybe many of you heard about. But yeah, so I think this, for example, here, I forgot where it is. So the magnetics or spintronics is one research area that I'm also working on. And we are trying to use nanomagnets in order to make them as neurons and synapses, okay? But then one downside of it is compared to other candidates, they have very low like on-off ratio. So when you have like a high, like maximum conductance state and the low conductance state, okay, so this window is supposed to be very big, but for spintronic materials, unfortunately, this is very low. But other than that, they have very nice characteristics like energy efficiency, speed, scalability, how small it can be, they are much, much better than the other technologies. So I think, if we can find out some way to make this window even bigger, that's gonna change the game. And you mentioned race-track memory, but I think that's more for conventional storage. And as far as I know, that race-track memory has not been used for AI yet. So that was more for conventional type of storage device that can replace your flash memory, for example. But they can give you better speed and better storage capacity and all that, but shouldn't have anything to do with AI chip for now, in my opinion. I may be wrong, but that's what I think. Yeah, it's a little kid. Side problem. Oh, is it a good question? Yes, I mean, you're right. So in many science and engineering problems, let me answer that way. So unfortunately, but I mean, it's unfortunate, but that's how, I mean, all these things, makes our life very interesting, because when you make one thing better, like energy efficiency, and you increase the energy very much, okay? If you improve one thing, then there is very high chance that you lose something else, because there is always like engineering trade-off, like you have to sacrifice something in order to get something else. So in electronics, if you say, so you get your energy efficiency, I mean, let's say your energy very, very low, okay? So then because your energy is so low, so it's probably possible that your material is not reliable enough, okay? Because any small energy can change its status, for example, okay? So maybe it's good in terms of energy efficiency, but it's bad for something else. So I think it's always our job to find the optimum and balance between all different things that we want to achieve, but it's been always challenging, and that's why we need some brilliant people and brilliant ideas from maybe the next generation. Yeah, thank you for that question. Yeah. Any other questions?
More open questions. That will conclude our session for tonight. Any questions on the way out the door if you left? Otherwise,